bursting. Now, fail-safe and fail-safe. A valve can fail open or fail close. The AS, let me rub that out. The AS 1101.6 official symbol for fail close is this, and the official symbol for fail open is that. They're the official symbols, I think. I always get them mixed up. And that's one of the reasons why I would not recommend you to use the official symbols, because everybody gets them mixed up. They're stupid symbols. What's almost universally been adopted instead is to write underneath the valve fail close or fail open. It's not the sort of thing you want to make a mistake at. I always had this vision of these two blokes driving away from Chernobyl, and one of them saying, you know what, I always got those two mixed up. You don't want to make a mistake with this. The rule we have for valves, for fail-safe, is that, let me get a pen, you remove the source of the energy, and then you remove the energy. That's the rules we have for valves failing safe. So that let's give myself, here I've got a boiler. Oil goes in it, and I've got, I'll tell you what, I'll do it in a different colour. I've got water going through that boiler. So I've got water going into this boiler, and I've got oil going into this boiler. I've got two valves. Right. What shall I fail the oil valve to? No, it's not lube oil, it's an oil-fired boiler. Yep, the oil valve fails close. And what about the water valve? The water valve fails open. Now you might say it's a bit wasteful on water. Well, not half as wasteful as if the valve failed close and the oil-fired boiler cracked right down the middle. That's very wasteful. So, we remove the source of the energy, which is the oil, and then we remove the energy. We use the water to remove the energy, to cool the boiler down. That's the rules we have. Which leads me onto electrical actuators. We had in the 80s and 90s, and still ongoing in some industries like air conditioning, we had this flirtation with electrical actuators. Generally speaking, what you're talking about is an actuator which has got a 24-volt DC motor inside it. The only way you can get an actuator that's got a 24-volt DC motor inside it to open or close any decent-sized valve is by using an incredibly huge gearbox. Well, not huge, an incredibly geared gearbox, I should say. The problem with this is that a typical electrical actuator takes 6.5 minutes to stroke. That means it takes 6.5 minutes to go from 0% to 100%. Now that is very, very slow. The other big problem with an electrical actuator is it doesn't easily fail safe. There's two methods of getting an electrical actuator to fail safe. The first is to use a bloody great big spring. And this spring is like a clock spring, so it's a spring like this, and it winds up that spring, and then in the event of a power failure, the spring lets go and shuts the actuator. There's supposed to be a clutch there, which is supposed to then release. But normally the clutch doesn't release enough, and as the spring winds shut, it also rips all the teeth off the gearbox. That's one method. The second method is to use a battery. To have a nice big fat battery sitting next to the valve. Well, let me tell you, the very last thing you want to find in the event of a fire is a lead-acid battery sitting there bubbling and boiling away to itself. That's if the battery didn't cause a bloody fire in the first place. So electrical actuators are okay for small industries, like home industries, like aircon, that sort of stuff. So they're okay for HVAC. Heating, ventilation and air conditioning, they're okay for that, but really not really for anything else. Now, I want to talk to you a little bit about something called split ranging. Split ranging is where we take a signal and we split it into two parts to control two valves, or maybe three valves. So in this case, there's two ways of doing split ranging. The first way is what we call the trivial example of split ranging. What I'm doing here is I'm controlling the temperature inside a whiskey tun. This thing here is a whiskey tun, and I'm controlling the temperature inside there. If it gets too hot, then what I do is I open up this valve here. This is my chilled water valve. Maybe I should write that in because you might not know. Chilled water, and this is hot water. So if my whiskey tun gets too hot, then I output a low signal below 60 kPa. So if it gets too hot, my output goes maybe 20-30 kPa, which opens up the chilled water valve. See, what I've done is I've set the first valve, the chilled water valve, I've set its positioner up to go 55 to 20. So that's 100% open. So the chilled water valve is set up that when it's 55 kPa, it goes 0% open, it closes. When I've got 20 kPa, it's fully open. So if I output a number which is less than 55, my chilled water valve starts to open, and I cool the tun. If it gets too cold, then I output a pressure which is greater than 65 kPa, and it starts opening the hot water valve. So what I've done is I've got this one signal, which is my 20 to 100 kPa signal, and I've split it. I've split the range in two halves to control two separate valves. Now that's one example of split ranging. It's the trivial example. It's not really used that much apart from, well, little jobs. The real reason we use split ranging is to improve a thing called our turn-down ratio. With virtually all valves have got a turn-down ratio of 10 to 1. What that means is, if the maximum controllable flow through your valve is 100 litres, the minimum controllable flow through your valve will be 10 litres. Now I'm saying controllable flow. Obviously the minimum flow through a valve is nothing. You've got the valve shut. But this is the minimum controllable flow. If you try and go less than the minimum controllable flow, you're going to be into cavitation and flashing. So that's what a turn-down ratio is. Most valves, you just take them to have a turn-down ratio of 10 to 1. Now we're going to do split ranging to improve that turn-down ratio. So here I've got split ranging, improving turn-down ratio. What I've got is two valves, and they're both the same size. So that's the important point. Valves identical. So both valves are identical. They're both the same size. Each one of those valves individually has got a turn-down ratio of 10 to 1. Now, let's say for the sake of argument I want to put 100 litres per minute through that combination system. That's my maximum flow. What that would mean would be 50 litres per minute going through that valve and 50 litres per minute going through that valve. So each one of these valves is capable of controlling a maximum of 50 litres a minute. So if it's got a maximum of 50 litres a minute and it's turned down, so that's valve A. If it's got a maximum of 50 litres a minute and its turn down ratio is 10 to 1, what's its minimum flow? Yep, you've got it. It's 5. So valve A, the flow can go from 50 to 5, which is 10 to 1. But when both valves are open, the maximum flow is 100. So as a combination, the valves as a combination have got a turn down ratio. They can go up to 100 litres and down to 5 litres. So as a combination, we now have a turn down ratio of 20 to 1. So I've improved the turn down ratio to 20 to 1. Just out of curiosity, what do you think would happen if I stick a third valve on there? What would I improve the turn down ratio to if I stuck a third valve on there? Well, actually, let's have a look at the numbers. Say I want to put 100 litres through the whole thing. So that one can take, let's say, 30 litres. So the minimum flow, that will go 30 to 3. That one will go 30 to 3, or 33 to 3. 33 to 3. And this one will go 33 to 3. So the minimum flow will be 3. The maximum flow will be 100. 100 to 3 is, or 3.33, is 30 to 1. So every time I stick another valve on this, I increase the turn down ratio by another 10. Okay. So, just to make sure you've understood this, and I think you have, what is valve A doing? I need you to tell me what valve A and valve B, A equals and B equals, when the pressure is 40 kPa. Okay, you've got it. Valve A is at 50, valve B is at 0. Okay, let's do now valve A and valve B when the pressure is, I'm outputting a signal of 80 kPa to both valves. Now what are valve A and valve Yep, you've got it. Valve A is full open. Valve B is 50%. So, the important thing to remember is that they're not working simultaneously. They're working in series. It first opens valve A with valve B shut, and only when valve A is fully open does it start opening valve B. So they work in series. First valve A and then valve B. Not together. Okay. That's split ranging. We use it to improve